study the unit for work, energy and power. So here in this chapter we are going to study about the work, about the power and the energy. What we are going to cover is work is done by the constant force and a variable force, kinetic energy, work energy theorem, power, potential energy of a spring, conservative forces, conservation of mechanical energy, kinetic and potential energy, conservation and non-conservative force, concept of collision, elastic and inelastic collision, and in 1 and 2 dimensions. So these are the main basic topics which we are going to cover in this chapter. So let's start with the work. The work done is defined as a product of force and the displacement. We can define work as a product of force and displacement along the direction of the force. If the displacement is t, then makes an angle theta, then the force F, then W is equals to Ft cos theta with respect to any angle, or we can write it as work is equals to force into displacement. So mathematically W is equals to F into D, and when we write it in the statement, then work is defined as product of the force and the displacement along the direction of force. Thus, work is the dot product of the force and displacement is the scalar quantity with the dimensional formula ml squared t minus 2 raised to the power minus 2. The SI unit of work is joule, and always keep in mind that 1 joule is equals to 1 Newton into 1 meter. In CGS system, the absolute unit of work is erg, or 1 erg is equals to 1 dyne into 1 centimeter. These are some important things which we can use in our numericals, or maybe in objective form also will get some kind of question like this. Also keep in mind that 1 joule is always is equals to 10 raised to the power 7 erg. So this is about work. Moving to the next, we'll read about the energy. The energy of the body is defined as its capacity of doing work. Simply we use this word, right? The energy is something of a body. Any body is defined as its capacity of doing work is energy. Like work energy is also a scalar quantity. The dimensional of energy is same as that the work is ml squared t minus 2. It is measured in the same unit as the work, that is joule, and in SI unit or in CGS system. Now moving to the next, kinetic energy. Kinetic energy of a moving body is measured by the amount of work which has been done by bringing the body from the rest position to its present position. If any body is in rest and we are just simply providing the force and just bringing the body from the rest position to its present, then it's a kinetic energy. Now kinetic energy is equals to half into mass speed square. Now moving to the next, work energy theorem. According to this theorem, the work done by the force is displacing the body is equals to the change in kinetic energy, means W is equals to delta K. Work done is equals to displacing the body is equals to the change in kinetic energy of the body. Now potential energy. The energy of a body is due to the position of the rest or the deformation. What is potential energy? Energy when in a body due to the position of the rest or deformation is called potential energy of the body. Gravitational potential energy. W is equals to force of gravity, height, which is equals to mgh. So we can say W is equals to mgh, or U is equals to W and W is equals to mgh. This is the gravitational potential energy. Potential energy of an idle spring. The work W is stored in the spring in the form of elastic potential energy when it is of the stressed or the compressed spring. Any spring is there, whether it is stressed or whether it is compressed. Okay, but the work is stored in the spring in the form of elastic potential energy. This is the potential energy of an idle spring. Now the principle and also thus U will be equals to W half kx square. Principle of conservation of energy. According to the principle of energy, energy can neither be created nor be destroyed, but it can be converted from one form to another. The total amount of energy is the universe remaining constant. Okay, there are some points which we need to remember. That concept W is equals to Fd, F is equals to ma, then W is equals to mad, right? We can write it as the value F is equals to ma. Also work is interpretation, m is mass, a is acceleration and d is the distance. Now moving to the next, power. the rate of doing work by an agent or a machine is called power. We are doing work, but by whom? By any agent or by any machine, then it is called power of the agent or power of the machine. Power is always is equals to work upon time. Whatever work is doing with respect to the time is always is equals to power. SI unit of work is joule. The SI unit of power is joule by second. This is called watt, and if 1 joule of the work done is 1 second, the power is 1 watt. Or we can write 1 watt is always is equals to 1 joule per second. This is about the power. Now conservative force. Conservative force is that force by which work done depends on the start and the end of the position. Work is defined but from the start and end of the position of the object and not on the path followed. This is the conservative force. This page is representing something which we are going to study in the whole chapter: work, power and energy, capacity of doing work, types of mechanical energy, work, power, collision, type of work, positive work, negative work, zero work. These all topics we are going to cover in this chapter. Now, non-conservative force. Also example of conservative force is gravitational force, elastic spring restoring force, electrostatic force, buoyancy force, etc. Non-conservative force. Non-conservative force is that force by which work done depends on the path of followed by the object. Example is friction, air resistance, non-elastic material, stress, resistance to the flow of electric current, etc. Now collision. Collision between the two bodies. We have two bodies, like we have A, okay, and another body is B. So when there is collision, when they collapse, then they said to occur, they are either physically strike against each other, or if the path the motion is one, then influenced by other. This is what collision called. There are two kind of collision. One is elastic, another one is inelastic. So an elastic collision is the collision in which there is no net loss in kinetic energy. Keep in mind, in elastic collision there is no net loss of kinetic energy in the system as a result of collision. When there is collision, it's fine, but also in the result there is no net loss in kinetic energy. Both momentum and the kinetic energy are conserved. This is what elastic collision called. Inelastic is something, and inelastic collision is collision in which there is a loss of kinetic energy. The momentum of the system is conserved. It's fine that momentum is conserved, but and there is loss of kinetic energy. Whether in the elastic collision we have read that there is no loss of net kinetic energy. So this will be elastic. When there is loss of kinetic energy, this will be inelastic. Now key equation and the formula. Always keep in mind, the work done is equals to F into S, or F is equals to S cos theta. F is the force, S is the displacement, and angle theta is the angle between them. Next, work done by the variable force, then W is equals to F dot ds. Kinetic energy K is equals to half of mv square. M is the mass, B is the velocity of body. Work energy theorem, W is equals to delta K. Work is always is equals to change in kinetic energy. So W is equals to delta K. Gravitational potential energy U is equals to mgh, where m is the mass, g is the acceleration, and h is the height above ground. Potential energy of the spring U will be equals to half k x square. K is the spring constant, x is the extension of the spring. Power P is equals to W upon T. We can write F is equals to P is equals to F into B. F is the force, B is the velocity, W is the work, and T is the time. Elastic collision in 1D and elastic collision in 2D. Okay, but for there is only for the 1D. As we know that collision is between the two bodies, so we consider two bodies equation like m1 v1 like this. So for elastic collision in the 1D, v1 will be equals to m1 minus m2 upon m1 plus m2, its whole bracket, and then u1 plus 2 m2 upon m1 plus m2 and u2. You'll have to learn this by heart, this equation for the two different material or the bodies. Then v2 is equals to m2 minus m1, m1 plus m2, its whole bracket, and then u2 plus 2 m1 upon m1 plus m2, and then u1. So these are some key equations and the formulas. Now let's move forward with some questions based on these equation and formulas only. First question is, a body of the mass is 20 kg initially at the height of 3 meter. That's fine. above to the ground, it is lifted to a height of 2 meter. From that position, its increases in potential energy is. So see, we have mass is 20 kg, h is 3 meter. Potential energy of first one will find Pe1 is equals to mgh. Then we'll substitute all the values. We get Pe1 is equals to 588 joules. Height h is 5 meter. Okay, it means 3 meter plus 2 meter. Then Pe2 is equals to mgh. Then it will be equals to 20 into 9.8. Value of g is 9.8 into 5. It will be 980. As we'll have to find increase in the potential energy, then Pe2 minus Pe1. When we minus it, then we'll get the value of increase in potential energy is 392. It is increased by 392 joules. Now second one is two masses are there, m1 or m2 is 1 gram and 4 gram, and moving with the equal kinetic energies. The ratio of the magnitude of the linear momentum is, we know kinetic energy is equals to p square or upon 2m. Okay, now two masses are given m1 and m2, then k1 is equals to k2 we say. Then we'll substitute the value p1 square upon 2m1 plus p2 square upon 2m2. P, it's same for both, then we'll write p only, and then p upon 2 into 1, 2 into 4, then we get the value, it's p1 and p2. P1 ratio p2 will be equals to 1 by 2. When we solve this, it will be p1 and this will come here this side, we will go this side, and we get the value of p1 ratio p2, which is equals to 1 ratio 2. Now an electric heater is rating 1000 watt is used for 5 hours per day for 20 days. The electrical energy utilized is, when some electrical appliances are used in the energy utilized given by the product of the appliances and the time. We have given that 1000 watt is equals to 1 kilowatt as we know. So the time will be is equals to, we have already time 20 days, so 20 into 5 hours, then it will be equals to 100 hours. And electrical energy is equals to power into time. So electrical energy will equals to 1, power is 1 into 100, then we get total electrical energy equals to 1000 kilowatt per hour. Now there are some basic other questions like, can kinetic energy of a body be negative? The kinetic energy is half mv square as we already know. Cannot be negative as both m and b are always positive. Mass cannot be negative, v cannot be negative, so obviously kinetic energy cannot be negative. Can potential energy of the body be negative? The potential energy can be negative when the force involved is attractive. Okay, if force is attractive, then it can be negative. In which type of motion momentum changes but the kinetic does not? In a uniform circular motion, momentum changes but kinetic energy does not. Always keep in mind in uniform circular motion. So this is all about the 1 mark question. Moving to the next, we have 2 mark question. Explain the positive work and the negative work. See, if force is applied to a body, okay, on a body is in the same direction, it is just going in the same direction, force is applied, okay. As displacement of the motion of the body, the work done by the force is said to be positive, then W is equals to F cos 0 degree, it's going in the same, is of no angle, then 0 degree. Or we can write FW is equals to Fs. If the force act opposite in the direction of the motion, it's going in the same, that's fine. But if it is going in the opposite direction, okay, like this, then work done by the force is said to be negative because there will be the 180 angle, then Fs cos 180, it will be equals to minus Fs. So this is about positive work and the negative work. If two protons are brought towards each, what will happen to their potential energy if the proton and the electron can be brought nearer then? So the potential energy will increase because in bringing the proton nearer, it will increase. Why so? Because in bringing the proton nearer, work to be done against the force. When we want to work proton nearer, then we'll have to do some work, okay, and against the force of repulsion, which will be stored in the form of potential energy. So the potential energy will decrease. In this particular case, what will happen? Potential energy is utilized, but in this case, it is going to be decrease when the proton and the electron are brought nearer to each other. Now, moving to the 3 marks question. Does work depends on the frame of reference? Explain with a suitable example. Work depends on frame of reference. With the change of frame of reference, or we can inertial force does not change while the displacement may change. So the work done by the force will be different in different frames. We cannot say that it will be remain same, but yes, if different frame will be there, then obviously work will be different. Okay, the work done by the force will be different. Example, if a potter with a suitcase on his head moves with a staircase, work done by the upward lifting force relative to him will be 0, as the displacement related to him 0, while the relative to the person on the ground will be mgh. So this is the difference with the example, that it will be different with reference to the with respect to the different frames. Define energy, give unit and the dimension. We'll have to explain what actually energy is, and we'll have to also explain the units and the dimension. So the work done, the energy of a body is defined as its capacity of a doing work. This is what the definition of energy is. Since energy of the body is the total quantity of a work done, therefore it is a scalar quantity. It's a total quantity of the work done, therefore we can say it as a scalar quantity. Dimension will be equals to ml square t minus 2. It is the same as the work or torque. And unit will be equals to joule in SI and erg in CGS system. Practical units is electron volt EV or kilowatt hour, which is kWh, and the calories is CAL. So this is about energy, its unit and the dimension. Now another is 5 marks question. Derive the expression for an elastic potential energy. This is very important. Firstly, when a spring is stressed, we have one case, we have one spring and it is stressed or compressed, anything. From its normal position, x is equals to 0. Then the work has to be done by an external force. We have one spring, okay, like this, and just will have to stretch or will have to compress. Its normal position is 0 here. Work has to be done by the external force. Okay, when we apply any kind of force for stretch or compression, work has to be done. Then Fx means force, external force will be equals to minus of restoring force. They both will be opposite, which will be equals to Kx. K is the constant and x is the displacement. Now let the spring is further stressed through the distance dx. It is again going to be distress from x to dx. Then the work done dw will be equals to F external dx is equals to F external dx cos 0 degree angle is going to be made, then it will be equals to kx dx. This is the first, when it is going to be stretched what dx. Therefore the total work done to stretch the spring through a distance x from the main position will be w is equals to from 0 to x, as it is a 0 when it is going to be displaced, then there is x. So from 0 to x will be the limit dw, then x to 0 will substitute the value kx dx, then when we integrate it kx square, then x goes to 0, we get half kx square. This work done is stored as a potential energy in the stretched spring. So elastic potential energy U will be equals to half kx square, or you can write half U is equals to half fx, as k is equals to f upon x. So it will be equals to fx only. U is equals to f square upon 2k. Then elastic potential energy will be equals to U half kx square, or half is equals to fx, or we can write it also as f square upon 2k. So this is the final result for elastic potential energy. This is the expression for elastic potential energy, that U is equals to half of kx square. Also we can write it as half fx, or we can write it as f square upon 2k. Now moving to the next, explain the different type of collision in detail, give example to support your claim. Firstly, we are going to differentiate 3 type of collision. It's perfectly elastic collision, inelastic collision, and perfectly inelastic collision. Okay, let's read. Firstly, it's perfectly elastic collision. If in a collision, kinetic energy after the collision is equals to the kinetic energy before the collision. Okay, there is collision, that's fine, but before and the after collision kinetic energy is same or equal, we can say the collision is said to be perfectly elastic, that's fine. But for the inelastic, if the collision of the kinetic energy after collision is not equal, here it is equal but here it is not, as word represents, it's inelastic. to the kinetic energy before collision, then it is said to be inelastic. Then perfectly inelastic, what is it? If in a collision two bodies stick together or move with the same velocity after the collision is said to be a perfectly inelastic. This case is fine, but two bodies are just stick together and they are moving with the same velocity. Velocity is not v1 v2 for them, it is just only v for them even after the collision, then it is said to be a perfectly inelastic collision. Here coefficient of restitution will be equals to 1. Coefficient of restitution will be 0, e and 1, it will be between 0 1. Coefficient of restitution will be 0. Now Ke final will be equals to Ke initial. Mathematically we can express like this. Here kinetic energy appears on the form. In some cases Ke final is less than Ke initial, such as in initial K is converted into the internal energy of the product as a heat, elastic or excitation, than while other case Ke final is greater than Ke initial. So it depends on the case. The term perfectly inelastic does not necessarily mean that all the initial kinetic energy is lost. It implies that the loss of kinetic energy is large as it can be consistent with the momentum of conservation. Now let's read with the example. Collision between atomic particles. This is the perfect elastic collision example. Bouncing of a ball with the same velocity after the collision with the earth. A collision between the two billiard balls. Second is collision between the two automobiles on the road. In fact, majority of collision belong this category. The accidental thing is an elastic collision. And example for this perfectly inelastic is collision between a bullet and a block of a board into which it is fixed. When it is bullet remain embedded in the blocks. So this is all about the different type of collision in detail and with the example we have claimed. Now moving to the next, we'll read some numericals. We have a force act on the 30-gram particle in a such way that the position of the particle function time. We have one equation for function is given, x is equals to 3t minus 4t square plus t cube, t cube, where x is the meter, t is in the second, and what is the work done during the first 4 seconds we'll have to find. So we know that velocity is equals to displacement upon time, and it will be equals to 3 minus 8t plus 3t square. When we just differentiate this, okay, we get v0 is equals to 3 meter per second and v4 is equals to 90 meter per second. Okay, so here w is equals to half mv4 minus v0. Why v0 and v4? As we'll have to find the work done for the 4 seconds, so it will be between 0 to 4. Then according to the work energy theorem, it will be half. When we substitute the value, we get 5.28 joule. This will be the work done during that first 4 seconds. Now force of 5 Newton act on the 15 kg. Initially at the rest, what is the work done by the force during the first second of the motion body? So W is equals to Fs, which is equals to F into half AT square. As we know, S is equals to UT plus half AT square. This is the second equation of motion. When we just simplify this equation and put all the values, we get F square T square upon 2M. Then 25, whatever values we have, like we'll have to substitute it. 5 is square 25, 1 is square 1, 2 into 15, then we get 5 upon 6 joule. Another is two bodies A and B having the mass of the ratio is 3:1 possess the same kinetic energy. What is the ratio of their linear momentum? We know P is equals to whole square root of 2me, or P1 upon Pt is equals to square root of m1 upon m2. Then P1 upon P2 is equals to 3 under root of 3 upon 1. This will be the ratio. Now our weight lifter lift 300 kg from the ground to the height of 2 meter in 3 seconds. What is the average power generated by him? We know that power P is equals to work done upon time. Then work done is equals to mgh upon t, which will be equals to 300 into 9.8 into 2 upon 3, which is equals to, when we substitute the value and we calculate it, we get 1960 watt. Okay, this will be the power or the average power generated by him. Now one graphical question is also there. A force F is acting on an object where is the distance x. The force is in the Newton and x is in the meter. What is the work done? Why the force in the moving object from x is equals to 0 and x is equals to 6 meter? We have this graph. So work done is equals to area enclosed by fx graph, okay, which is equals to area square here we can see it's the area of a square and as well as triangle. This will be equals to the sum of area of a square and area of triangle. So this will be equals to, we substitute the value of area of a square, 3 into 3 plus half, 3 into 3. When we solve it, we get 13.5 joules. So the work done will be equals to 13.5. Now, two particle of masses m1 and m2 in projectile motion have a velocity v1 and v2 respectively at t is equals to 0. They collide at the time t is equals to 0. Their velocities become v1 dash and v2 dash at the time 2t naught. Then while still moving, what is the value of this? This we'll have to find. So the momentum of the two particles is t is equals to 0. Then p1 is pi is equals to m1 v1 plus m2 v2. Collision between the two particles does not affect the momentum of the system. Then a constant external force m1 plus m2 g acts on the system. The impulse by the force t is equals to 0 to t is equals to 2t naught is m1 plus m2 into z and 2t naught. Then change of the momentum will be equals to 2 plus of m1 plus m2 and then gt naught. Now we have some case based question. Case is given and with respect to that case we have some questions as well. See, read the following text and answer the following question on the basis of it. Clockwork refers to the inner working of a mechanical clock or watch where it is known as movement, a different type of toys which is work using gears driven by the spring. Clockwise device is completely mechanical and its essential parts are a key or a crown which you bind up to energy, spiral spring in which energy is stored, a set of gears through which spring is energy is released. The gears control how quickly or slowly a clockwise machine can do things such as mechanical clock, watch, and the mechanism is set to the hands that sweep and around the dial to tell the time. If a clockwork car, toy, gears drive the wheels. Winding the clockwork with a key mean tightening a sturdy metal spring. Call its mainspring. It is a process of storing the potential energy. Clockwork springs are usually twist of the thicker steel, tightening them and then forcing the spring occupy the smaller space is actually the quite hard work. Within it is just simply the case which is storing the potential energy, but how it's only showing. With each turn of the key, fingers of potential energy is stored in the spring. The amount of energy stored depends on the size of the tension spring. Harder a spring is to turn, or longer it is bound to more energy it stores. Okay, and while the spring uncoils, the potential energy is converted into the kinetic energy through the gears, clamps, and shaft, which allow wheels to move faster and slower. In the ancient clock, gears transform the rotating shaft and it drives the second half at the one speed, the minute hand 1/60 of the speed, and the hour hand 1/3600 of the speed. Clockwork toy cars often use gears to make themselves race along with the surprising speed. So this is the case very clearly. Like all the things has been mentioned. Now on the basis of that we'll have to answer. What is the meaning of movement of old age mechanical clocks? Here we have four options. The gears which moves the hand of the clock, a spring and the combination of gears which move hands of the clock, the hands of the clock, or the pendulum clock. So here movement of a movement, as obviously we have in spring as an object. Okay, so movement refers to the inner working of a mechanical clock using the series gears driving by the spring. That's why here from the rest of the three only B option will be the correct, as the spring and the combination of gears which is moved hand on the hand of the clock. Which type of energy is stored in the spring while binding it? So winding is the spring means tightening a sturdy metal spring. It is the process of the storing potential energy, forcing a spring to occupy the much smaller space. Is actually a quite hard work. Within each turn, key fingers do the work of potential energy, so it is stored. So we can say that potential energy is going to be stored. Now another case is when a spring of the clockwork uncoils, when the spring of the clockwork is uncoiled, then what will happen? In this case, potential energy is converted into the it's not been tightening here. In this case, it's getting uncoiled. Then when the spring uncoiled, the potential energy is converted into the kinetic energy through which gear, cams, cranks and the shaft, which allow wheels to move faster or slow. When it uncoils, then option B will be the correct. So this is all about some cases. Also, let's move to the fourth one. In the clockwork device that transform the speed of the rotating blanks to drive wheels slower or faster. In ancient clock, gears transform the speed of rotating shaft and it drives the second hand and the one speed of the minute, which is 1 by 60, and 1 hour is 1 by 3600. Okay, then of that speed, clockwork toy use the gears to make themselves race and surprising speed. So in clockwork devices, gear transform the speed of rotating shaft. One shaft is going to be rotate and gear transform the speed, the wheel slower or faster. They both are playing the role gear in the shaft. Most energy is stored in the spring if spring is larger, harder, bound for the longer time, then energy will be stored. When with each turn of the key, fingers do work and potential energy is stored in the spring. The amount of energy stored depends on the size of the tension and obviously size of the spring. Harder the spring is turned, the longer it bound and the more energy is going to be stored in this. Now, like this, we have some more subjective question, and on the basis of that we'll have to answer it. Okay, now this is the assertion and the reason based question. We have assertions and the reason. We'll have to determine whether both the assertions are correct, whether A is true or B is not, whether A is true and B is dependent on A as well. A is false, R is true, like this. So it depends on assertion and reason. Like this first one, we have assertion, mass and energy are not conserved separately. They are conserved as a single entity called mass energy. That's fine. Reason is mass and energy are interconvertible. So yes, mass and energy are interconvertible. We can convert it. That's fine. Which means B is the correct. Okay. Now moving to the A. Yes, mass and energy are not conserved separately. They conserved as a single entity, mass energy. We can conserve them it as a single entity. So according to the Einstein theory, mass of the energy is equals to mc square. We know. So mass and energy are conserved separately. They are conserved as a single entity. Hence, assertion and the reason both are true, and explain the assertions as well. Like this, another one is the kinetic energy of the body of the mass is 2 kg and the momentum is 2 Newton second is 1 joule. Then the reason is the relation between kinetic energy and linear momentum of an object is given by k to m. Then obviously they both are not readable, but let's see. K is equals to p square upon 2m. Then k is equals to 2 square upon 2 into 2 means k is equals to 1 0. So assertion is true, that is fine. But when we come to this, no, the relation between the kinetic and the linear momentum of the object is given by this. No, this is not the relation between both of them. So here we can conclude that both A and B, here we can conclude that A is true. That's fine. We have simplified. Okay, concluded. But R is not true. This is not correct. Now, another is a spring. Assertion is a spring stores a potential energy when compressed as well as stressed. So the reason is potential energy is stored in the body by deformation at shape. Obviously, they both are correct. When a spring is compressed or stressed, shape is deformed. We know. Hence, the elastic potential is stored in it. So, assertion, the reason both are true, and explains the assertion as well. So, this is all about this chapter work, energy and power. And on the basis of some formulas, we have studied W is equals to FD and all. You will have to find these. You'll have to take this self-assessment paper as well. So, this is all about for the chapter 4. Stay tuned for the chapter 5. Thank you.